So this is our last topic, and this is on flywheels. So as you see here, so this is a single cylinder engine, this is the connecting rod, and this is the crankshaft, and these are some counterweights. These two are the bearings, and this is also the part of the crankshaft. This is the crankshaft, and here we put a flywheel. And why do we put a flywheel? Because we know that the torque generated in this engine is a varying torque. So now if you look at this flywheel, so this torque is actually coming from the engine, and this is the load torque. So if this is a varying torque, and if we assume that the load torque is constant, then at some portion of the engine cycle, this flywheel will accelerate, and in some portion it will decelerate. So there will be a fluctuation of speed. To keep the fluctuation of speed within a limit, we use a flywheel. So here, so you know that T minus TL, so you know that T minus TL is equal to I alpha, and I alpha is I d omega dt. So we write it like this: I d omega d theta dt. So we write it as I. So this is actually omega. So I omega d theta. So we write it in this form. So T minus TL d theta is I omega d omega, and if you integrate it, in the right hand side you get half I omega square, and in the left hand side you get T minus TL d theta. So if you integrate from a to b, then this is I omega square to b. So this is half I omega b square minus omega a square. So here actually the turning moment diagram of a steam engine is given. So 360 degree, that is one complete revolution. So it starts from here, sorry, it starts from here, or where? No, sorry, it starts from here. This is 0 degree, and this is 0 degree, and this is actually 360 degree, and this portion is actually this portion. This portion is actually this portion. So it starts here and goes up to 360 degree, which is here. So this is one cycle, 0 to 360 degree. Then see, it's again repeating, it will again go up, and this cycle will continue. So and see, for a steady operation, what will happen is, what is required is this: the mean torque from the engine should be equal to the load torque. That means here this TL should be the mean torque. Okay, then the mean velocity will remain constant. Though there will be fluctuations in velocity, the mean velocity will remain constant. That is, the mean torque is equal to the load torque is required for a for maintaining the mean velocity a constant. So this is the turning moment diagram of a steam engine as we have shown. So now if you find out the mean torque, how do you find out the mean torque? You find out the total area under this graph and you divide it by 360 degree, that is 2 pi, and you get the mean torque. Now these are the points where the turning moment T becomes equal to the mean torque. So A, B, C, D and E are such points where T is equal to Tm. So if T is equal to Tm, then you just see this relation. If T is equal to Tm or TL, then I omega d theta is 0. And if omega is non-zero definitely, then d omega d theta is 0. That means there you get, if you plot omega in this diagram, then here where this intersection, where this T becomes Tm, here the slope of d omega d theta is 0. So see, all the points where T is equal to Tm, the slope of omega versus theta diagram is 0. See, these are the points. So Tm is total energy output in a cycle by angle of a cycle, and total energy output is nothing but T d theta. Total energy in a cycle is T d theta, and this is over a cycle. So a 4-stroke engine, 2 revolutions make 1 cycle, and for 2-stroke engine 1 revolution is 1 cycle. For inertia torque, the total energy output is 0 in a cycle and even in a revolution. So if you think of a revolution, the total energy output due to the inertia torque is 0. Not only in a cycle but also in a revolution. So here you see the turning moment diagram for a single cylinder engine, 4-stroke single cylinder engine. So the cycle is from 0 to 720 degree, that is 2 revolutions. So this is suction 0 to 90 degree, then compression, this is this is suction 0 to 90 degree, zero to 180 degree, 180 degree to 360 degree, 360 to 540 degree, and 540 degree to 720. Yes. So 0 to 180 degree is suction, 180 degree to, so here to here, oh not here to here, this is 0 line. Yes, this is the 0 line. So here to here is suction, here to here is compression, then 360 to 540 is expansion, and 540 to 720 is exhaust. So this is a 4-stroke engine. So 2 revolutions make 1 cycle. Now see, and if you take the, so see, there is a difference between the 0 torque line. So this is actually the 0 torque line. So do not get confused. This is the 0 torque line and this is the mean torque line. So while calculating the total energy output in 1 cycle, you find out the T theta diagram with respect to the 0 torque line, and that T d theta integration over a cycle, you divide it by 4 pi and you get the mean torque, which is actually this. This is the mean torque line, and where the T curve intersects this mean torque line. Actually, these points are B, C, D, E, F, G. and at these points you say you get a zero slope in the omega theta diagram. So here let I be the mass moment of inertia of the flywheel. Omega m is the mean speed of rotation. Omega 1 and omega 2 maximum and minimum speeds of rotation. You can also call it omega max and omega mean, whatever you like. This EI is the indicated work per revolution of the crankshaft, not for a cycle. This is for per revolution. And Ke and Ks are coefficient of fluctuation of energy and speed respectively. Then EF is actually this coefficient of fluctuation of energy into EI. And the change of kinetic energy of the flywheel from point 1 to from maximum to minimum, this is actually maximum and this is minimum, is this. Here we take omega 1 as maximum and omega 2 as minimum. So omega 1 square, this is maximum, or you can write it as omega max square minus omega mean square, or rather, yeah, so if it is omega max square minus omega mean square half I, so then we call this the fluctuation of energy. And so okay, so actually ignore this line, there is some confusion here, this may create confusion. So what you can do is you do like this. So up to this it's okay. Then suppose omega max is your, suppose this is omega max is the maximum speed and omega mean is the minimum speed. Then what is the maximum fluctuation of energy? The maximum fluctuation of energy is half I omega max square minus omega mean square. So this is the maximum fluctuation of energy, or EF. Okay, so omega max, then this can be written as half I omega max minus omega mean and omega max plus omega mean. And then if you Ks, Ks is the fluctuation of speed, this is omega max minus omega mean divided by the average omega, or omega, which you call omega small m here, you can also call it omega average. So this is half I Ks, and this you can approximate as twice omega average. This omega max is above average, omega mean is below average, and for a small variation you can approximate it as twice omega average. So this is half I omega max, so you bring one omega average here, and so you divide it by omega average and you multiply it with omega average, then 2 omega average square, and this becomes Ks. So I Ks omega average square is the fluctuation of energy, and the fluctuation of energy is equal to coefficient of fluctuation energy into indicated energy per revolution, not per cycle. This you can write as omega average. So do not get confused with the notations. There are actually three quantities, omega max, omega mean and omega average. You can call it omega 1, you can call it omega 2, and we can call it omega n. And this is an important formula, that EF is the fluctuation of energy. Fluctuation of energy is nothing but half I omega max square minus omega mean square, because that is the fluctuation of energy. The maximum variation of energy possible is this, which is the fluctuation of energy. So let us now investigate a single cylinder engine 4-stroke. So again, this is, as you know, this is the suction stroke, this is the compression, this is expansion, and this is exhaust. And so this is the zero torque line, and T d theta divided by 4 pi gives you this red line, which is actually the mean torque line, and the mean torque has to be equal to the load torque if you want your overall velocity to be constant with fluctuations. So now this T cuts this mean torque line at this point, at this point, at this point, and at this point, this point and this point. So this point we call B and this point we call C. Now see, if we consider the energy, total energy at this point to be EA. So here the energy is EA. Now here what happens? Here what happens? So here energy is EA. So now energy is getting subtracted from EA because the available torque is less than the mean torque. Since the available torque is this one, is less than the mean torque, the energy of the engine is decreasing. And how much is it decreasing? That is T d theta, this blue one, this T d theta from A to B. So A to B, T minus Tm d theta, T d theta, not T d theta, this is T minus Tm d theta from A to B is half omega B square minus half omega A square. So here this, and this is EB minus EA. So EB minus EA is half omega B square minus half omega A square is minus A1. So what is the energy at B? Half omega B square. What is the energy? Because see, because this I is actually the moment of inertia of the rotating part of the engine, but since the flywheel moment of inertia takes the lion's share, so this can be taken as, this can be approximated as the moment of inertia of the flywheel. So here the energy is half I omega B square, here energy is half I omega A square. So this is T minus Tm B to A, and it is negative area. It is negative area because energy of B is less than energy of A. So this has to be negative area. And from here also, since T is below Tm, you understand that this is a negative area. So E at B is equal to E at A minus A1. Now E at C is E at B plus A2. What is the A2? A2 is the red portion. So that is EA minus A1 plus A2. And E at D is E at C minus A3. A3 means from C to D. So, and that means EB plus A2 minus A3, and that means EA minus A1 plus A2 minus A3. And if you combine this, this gives you 0 and you get back the same EA. So energy at A and energy at D are same because they are virtually the same, they are the same point. Now one example. The turning moment diagram for a multi-cylinder IC engine is drawn to the following scale. 1 centimeter is 15-degree crank angle, 1 centimeter is 3 kilonewton meter. That means one is along this 1 centimeter 15-degree crank angle, it is the theta direction, and in the torque direction 1 centimeter is this. During one revolution of the crank, the areas with reference to the mean torque line are 3.52 minus 3.77. This is the mean torque line that they have already mentioned here. Is the mean torque line. So above mean torque line 3.52 minus 3.77, 3 points. So this is 3.62, not 4.62, as this is 3.62, 3.35, 4.40, 3.42. So if you consider the energy here at EA or E, then energy at B is EB is E plus 3.52. Energy at C is EB minus 3.77, and that means E plus 3.52 minus 3.77, that is E minus 0.25, and energy at D is E plus 3.52 minus 3.77 plus 3.62. So this is E plus 3.77. Then energy at E is plus 3.52 minus 3.77 plus 3.62 minus 3.35. 3.62. Energy at E is 3.35, I suppose. This is 3.35. 3.37 minus 3.35. So there is some calculation mistake, I think. So one thing you can do, first 3.52 plus 4.62 plus 3.52 plus 3.62 plus 4.40 minus 3.77 minus 3.35 minus 3.42 should give you 0. So you should check that whether this data is correct or not. Oh, this is not 3.35, it is 4.35, sorry. So this is 4.35. Yeah, now I think it's okay. So this is E minus, okay, and then plus 4 point, so this is actually 4.35. This is 4.35 and not 3.35. So I think this is correct. So this is 4, but again you have to check it whether the plus ones, the sum of the plus ones is equal to the sum of the negative ones. So this, then 4.40, this, and you get back this. So again from starting from E, you should get back E. Now among all these values you find out the maximum. The maximum is 3.3 plus maximum is 4.40. So plus maximum is from here, plus maximum is this plus 3.52 plus 3.37. So this is plus maximum. So this is E max. And which one is minimum? 3 minus, this is minus 0.25, minus 0.98 E. So I think minus 0.9, this is E mean. So this is E max and this is E min. So if this is this, then this is the maximum, E plus 3.42 or 52. Oh, sorry, this is not the maximum. I made a mistake. Here. How can this be maximum? This cannot be maximum because this is 3.42 and this is actually maximum. So what is the fluctuation of, here you see what is the fluctuation of energy? E max minus E min. E max minus E min, and that is, so E max minus E min is the fluctuation of energy. So del E is equal to E max minus E min, which is half I omega max square minus omega mean square. Anyway, and that is equal to, and uh, here the overall fluctuation of speed is 2.5% on either side. So 2.5% is the fluctuation of speed. Suppose the fluctuation of speed is like this. This is the mean speed. This is the mean speed, and this is the fluctuation of speed. And from both side, in one side it is 2.5%. So if you consider both the sides, it is 0.05. And engine speed is this. So it is in this radian per second. So now you know what is ks and what is omega m. So delta E is half, is I ks omega square, and this is omega average square or omega mean square. So omega average and omega mean, no difference. So here it is actually omega mean or omega average, whatever. So this is omega average. This is omega average. So now you put the value of delta E, so 3.52, and you use the scaling, use the scaling 1 centimeter, 1 centimeter square is 1 centimeter square is, find out the radian value corresponding to 15 degree. So 1 centimeter square is this 3 kilonewton meter into radian value corresponding to 15 degree. And yeah, 1 centimeter square is 3000 newton into pi by 180 into 15 is equal to 785 newton meter. So you multiply this Emax minus Emin. Emax minus Emin is this minus this, and you multiply it with the 1 centimeter square, the value of 1 centimeter square, and you get this, and from here you find out the value of I. So let us stop here. Again we will continue with other examples.